Yes, I should. Do you see my screen?
Yes, perfect. Thank you. Go ahead, Christophe.
Thank you. Good morning, everybody. My name is Christophe PEYRARD. I am part of the research department of EDF. And here I will present you a work made with my colleague Maria Teles and also colleagues from France Énergie Marine. The objective of the work is to talk about the behavior of floating wind turbines in high seas, generating breaking wave loads. Here, what we were interested in was to characterize the position and the velocity of the vertical columns that compose a floater when they are submitted to breaking wave loads, in order to see what is specific to floating wind turbines as compared to the work already done on bottom fixed structures. So my presentation will first consist in giving you some idea of the site conditions we have considered in the DIMPACT project. Then I will explain the 10 megawatt systems that we have investigated to characterize the response of floating bodies in waves. After that, I will move to the breaking wave identification. So I will present a strategy that was used at the early phase of the project to detect breaking waves. And after that, I will focus on some outputs of the study. I will not show the study of all parameters, but I will focus on the velocity of the columns, which is, I think, quite specific to floating wind. So let's start with the site conditions. So we have investigated 3 site conditions within DIMPACT and look at the 50-year contours in order to capture the most severe loads. So we look at the Mediterranean Sea conditions, which is south of France. So mostly calm waters, but sometimes quite steep. We have looked at the Med Center conditions in Norway. So the Med Center is a demonstration site where Zephyros, for example, is installed, or Tetraspar. And last, we have considered the Brittany conditions, so west of France in the Atlantic conditions, so quite severe site. And what we did is that we extracted from the 50-year contours the most, the steepest conditions, and we make simulations, numerical simulation of the sea states. Quite a lot of simulation, I would say, because we needed to have statistics about the response of the floaters. So I will come back on these points later. But basically, what we tried to look at was the potential misalignment between wind and waves, given a steep sea state. Now let me present you the floaters and their response in waves. So within DIMPACT, we have investigated 4 floating solutions that was quite relevant of the market today. We look at TLPs, so EDF TLP, an academic design proposed by Milano in 2020, which is quite similar to the Provence Grand Large project that was installed last month offshore Marseille. So what is specific with this turbine is that the lines are inclined, so the motion of the floater is a bit specific as compared to a more classical TLP. The second TLP we have investigated was an academic DTU TLP proposed by Logesen and Hansen in 2015. So quite a typical TLP with vertical leads, with a very large cylinder in the middle of the floater. Also, we investigated the Nautilus semi-submersible proposed during the Life 50 Plus project that was used here without the active ballast activated, and also a SPAR developed by EDF in 2018, because SPARs are quite significant regarding the market today. So all these designs are applied to the DTU 10 megawatt turbine. So the academic and well-known 10 megawatt turbine proposed by DTU. Regarding the modeling assumptions, I will not go into too much details, but we use quite state-of-the-art methodologies with turbulent wind using TurbSim, irregular waves using the ERI, so linear waves on the stretching models. The turbine is flexible, so the blade can have a deformation in order to limit the wind loads. The tower is flexible also, the floater is rigid, and the mooring lines can be modeled in dynamic for the TLP or mostly in quasi-static for the spar. So the study was considering a lot of sea states. We considered 6-hour sea states on about 7,000 sea states for each floater in order to cover the 3 sites. To have a several sea state realization for each HSTP we consider, and to investigate also the misalignment between the wind and the wave. So it led to a lot of calculations, but this allows us to have reliable statistics. And it was not too long to perform using the supercomputer available at EDF R&D. So we think we have a quite representative behavior of the floaters in various environments. In order to check the relevance of the numerical models, we look at the production of the turbine because we realized that a lot of HSTP couples that we considered were associated to wind speeds allowing for production. So a consistency check for the calculation was to verify that we were following the DTU turbine production curve. What was a bit specific maybe to mention here was the development of specific controllers for the DTU TLP on the spar in particular in order to avoid the negative damping. So this is something that was done at the very early phase of the project. Maybe just to give you an idea of the floater response in wave, as I will talk about the velocity of the floater in the rest of the presentation, let me present the horizontal velocity arrows. So this is basically the velocity at the central column of the spar or of the TLP, depending on the wave period. And you see that for small wave periods, we have low velocity, so the floater is not responding to waves. And above 10 seconds period, we see that we have significant velocity that appears and tend to stabilize between 10 seconds and 15 seconds for most of the solutions. And if we look at the right figures, that give us the real and imaginary part of the velocity. The real part being the part in phase with the crest and with the maximum velocity in the crest. We see that the imaginary part is almost zero, and that we have a phasing between the velocity of the column and the velocity of the waves. So this is something that we will explore further in the rest of the presentation. Before moving to the results, I just wanted to come back on the breaking wave identifications that was used. So it was a strategy developed at the early phase of the DIMPACT project. I believe my colleagues will propose more up-to-date strategies in the other presentations. But basically here, what we did is that we estimated the phase velocity in the crest coming on the column based on the formula you see at the top of the slide. And we estimated the orbital velocity in the crest based on the Wheeler stretching, so basically using an elevation that is the mean sea level. And when the U over C ratio, so the ratio between the orbital velocity and the phase velocity, reach a certain level, we detected the wave as being a breaking wave. And after that, we look at the floater behavior under this specific breaking wave. So that gives us events of braking that we could analyze. So I will now focus on some output of interest. At the beginning of DIMPACT, we relied on the literature in order to quantify what is a severe braking event. We saw that the maximum force will depend on the phase velocity, on the crest height, on the curling factors, on different parameters. So all these parameters were investigated within the DIMPACT and using the time domain simulation I presented before. What I propose here is that we will just focus on the phase velocity. And the hypothesis we made at this stage of the project was to say that the relative wave body velocity will be the governing parameters instead of using just the crest velocity, what is done for bottom fixed structures. So I will now move to the results we got for the velocity of the floaters and for the phase velocity. So first, if we look just at the velocity of the floaters, here you have some plots with in green the density, the probability density of the velocities for all the C states. In red, you have the velocity for the peak events. So anytime a crest reaches a structure, you decide this is an event and you plot the probability density. And in blue, you have the density for the braking crest events. So what we see here is that, of course, when we have a crest, we have a velocity that is shifted as compared to the normal distribution that we can expect from a linear model. But the wave crest in braking events are even more severe and generating higher velocity for all the floaters we have considered here. So here we see the SPAR, the EDF TLP, and the Nautilus. And we see systematically that for braking events, the velocity distribution is centered on a higher velocity and explore higher velocity as well. So now we are not just interested in the column velocity, we want to look at the relative velocity between the celerity, so the phase velocity and the body velocity. And here you have some graph giving the body velocity in the x direction and the phase velocity in the y direction. And what we see from the response of various floater is that we have kind of a behavior with two lines. So the first one being quite steep for small phase velocity. We see that the body velocity does not change too much. So the floater is kind of not moving, not responding to waves. And for higher phase velocity associated to longer waves, we see that the floater is responding and it changes the slope of the tendency of the body velocity as compared to the phase velocity. So here we can feel that for very short waves and small waves, we will not have a response of the floater and will mostly consider the phase velocity to characterize the force. But as soon as we will have longer waves, we'll have to account for the body velocity. And it seems to be in the same direction as the phase velocity. So this is something we can see maybe more clearly on this graph. So in this graph, we plot in the x the relative phase body velocity. So this is the phase velocity minus the body velocity. And in y-axis, this is the phase velocity alone. And what we see from the different floaters we have studied is that the phase velocity is systematically higher than the relative phase body velocity, meaning that we can anticipate that the governing velocity that will be used for the forced characterization will be smaller for floating bodies than for fixed bodies. And we see that the distance between the phase velocity and the relative phase body velocity is bigger for bigger phase velocity, so for longer waves. So as a conclusion, just coming back on the main results, so we have investigating various type of floaters in braking sea-state conditions. So we have looked at the distribution of various parameters like the braking crest, the velocity, and we saw that braking events are very specific and are not just similar to any crest event or any event in the sea-state. So we need to investigate these braking events as a specific kind of events. We look mostly at the body velocity and at the pitch in the study. The tendency is to say that the relative velocity is lower than the phase velocity, so meaning that probably the loads will be reduced. And regarding the pitch, we saw also that we have larger pitch of the floaters for braking waves as compared to the typical pitch we can have for any crest in the sea-state. So we used the results in order to feed the basin test campaigns. So we determined the range of pitch and the range of velocity we wanted to apply to the basin model in order to investigate realistic braking configurations in DIMPACT. So I thank you for your attention.